In digital marketing, teams typically distribute budgets using static percentages or simple historical benchmarks. A company looks at what they spent last year, adjusts the ratios based on intuition, and applies those numbers to the new quarter. This heuristic approach functions well enough when resources are loose, but when total investment limits are strictly capped, the model fractures. You can no longer increase spend in one area without directly starving another. The tension scales when management introduces competing strategic objectives. Every dollar allocated to drive immediate lead generation is a dollar diverted from long-term brand awareness. Furthermore, platforms do not operate independently. The conversion rate on a search ad often relies on the broader awareness generated by a social campaign. If you cut the social budget, your search productivity drops. Spreadsheets governed by human intuition cannot explicitly calculate these trade-offs. The resulting financial decisions become opaque, subjective, and impossible to reproduce reliably. The alternative is to stop treating marketing allocation as a reporting exercise and formalize it as a constrained optimization problem. Scaling an operation under fixed constraints requires moving away from gut-feeling assumptions and executing the rigorous mathematics of operations research. This custom Python application organizes the optimization process into a pipeline with 6 distinct modules. It operates as a flow-locked state machine. Users must complete current parameters before moving forward. Once data passes, the gate locks shut behind it. This strict unidirectional flow serves a specific mechanical purpose. It forces the complete isolation of human strategic intent from the machine's mathematical calculation. Physically separating what the business wants from how the algorithm calculates the answer prevents informal, unstated assumptions from corrupting the final numerical output. The process begins by defining the executive requirements. A user enters their absolute total budget ceiling and selects their targeted marketing objectives. Next, the user selects the specific platforms they intend to utilize and assigns a strict priority ranking to each one based on its relevance to the business goals. The system takes these subjective UI inputs and runs a mathematical translation. Qualitative business goals are converted directly into hard numerical coefficients. The total budget limit is then applied over these variables as a solid boundary constraint. The algorithm cannot output a solution exceeding this sum. To prevent the algorithm from completely defunding an active channel, the user must also define the minimum spend threshold required to keep each selected platform operational. This entire setup phase forces management to explicitly quantify their strategy. Vague directives are eliminated before a single calculation takes place. With the strategy encoded, the system requires operational data. It ingests historical performance metrics for each platform, specifically isolating total past spend and total output generated. The application divides past spend by past output. This simple calculation yields a strict productivity ratio. This cost per unit metric acts as the primary efficiency coefficient. It dictates exactly how much output the algorithm expects for every dollar allocated to a specific channel. These construct the system's objective function. Its goal maximizes the expected output multiplied by the strategic priority weights. Notably, the application deliberately avoids using complex black box AI models to predict these performance metrics. Relying exclusively on simple historical ratios ensures that every step of the calculation is completely transparent. The final allocation is a mathematically auditable result, rather than theoretical guesswork. The calculation itself is executed by linear programming, utilizing a Python library called PuLP as its core engine. The engine evaluates decision variables. In this model, those variables represent the exact monetary amount allocated to each specific platform and objective combination. The global budget ceiling and minimum platform spends act as intersecting limits on a coordinate plane, creating a rigid bounding box. This shaded area is the feasible region. It represents every legally possible combination of budget distributions satisfying all constraints. The linear programming algorithm maps the objective function across the vertices of this feasible region. Because equations are linear, the optimal solution always exists at an outer corner. The algorithm evaluates each intersection, halting when it identifies the single vertex yielding the highest numerical value. The system extracts the mathematical coordinates of that final point and translates them back into a finalized list of dollar allocations. Mathematical optimality here is not a subjective best guess. It is the guaranteed peak output achievable strictly within the defined constraint space. If you remove the minimum spend constraints and run a pure, unconstrained LP model aiming for maximum efficiency, the system produces a highly concentrated allocation. The budget is dumped entirely into a single channel. According to the objective function, this is correct. If one platform has a slightly lower cost per unit than the rest, the mathematics dictate allocating every available dollar there to maximize total return. In practice, this creates massive operational risk. It exposes the entire strategy to extreme volatility if that single channel's performance suddenly drops. Pure mathematical perfection is incredibly fragile. Optimization algorithms require human-designed boundary constraints to force strategic diversification. To account for this fragility, the application utilizes a KPI forecasting layer designed to pressure test the optimal allocation against market uncertainty. The system splits the optimization model into 3 parallel tracks: conservative, base, and optimistic, adjusting the expected performance variables in each scenario. The raw outputs are passed into a decision interpretation layer. Here, the system translates the numerical matrices into an executive text summary. This module automatically identifies risks, highlighting areas of extreme budget volatility or dangerous overconcentration across the 3 tracks. The goal is to locate global stability. The application identifies specific allocation patterns that remain optimal, regardless of whether the future market proves to be conservative or optimistic. Ultimately, introducing operations research to business strategy is not about replacing managers with automated solvers. It provides an intellectually rigorous framework that measures, pressure tests, and justifies human strategic judgment.